All right. So in this module, we are studying edge-on spiral galaxies in the radio. In the first half of the module, we focused on Andromeda, the closest example of an edge-on spiral galaxy. It's our sister galaxy. It's so close that we can resolve it, even with our blurry single dish radio telescope. And so we decided to do Doppler imaging. Since we could resolve it, we made an image, but it was a Doppler image, so we can actually see its rotation in color, which is pretty cool. And then we did some calculations and learned a few things about Andromeda. In the second part of the module, we decided to focus on some galaxies that are farther away. These are also edge-on spiral galaxies. You can see the table here. There are 7 of them. And I asked each team to pick one easy one and one tough one. Okay. In the last video, we talked about that data and what it looks like. And just to review, let's look at one of them. This is one of the easy ones. This is the Sculptor Galaxy NGC 253. This is the on minus off divided by off spectrum. Here you can see the Milky Way hydrogen line, not perfectly canceled. A little bit of it still there. But then to the left of it, to lower frequencies, to the red shifted side, we see this broad emission, and that's the cold neutral hydrogen coming from the Sculptor Galaxy. Red shifted because the galaxy is moving away, and broadened because it's rotating. And that's an easy example. I just wanted to briefly show you some of the more difficult ones, and then we're going to calculate physical quantities about these galaxies. So here are the 3 difficult ones. This is Surfboard, and then we'll look at Hamburger and then Needle. So here's Surfboard, and it's tricky, but it's right here. This one, the broad undulations didn't perfectly cancel. Maybe it will when you observe it, but when I observed it for this particular case, it didn't in the one band, but it did in the other. It allowed me to see this little plateau. And this one's even more redshifted. Here's the Milky Way hydrogen line, and it's out here. Here's the next one. You can see it right here. Broad, shallow plateau. You can see it in both filters, in both polarization channels, I should say. Here's the other difficult one. You can see it right here. And let me go to live spectrum. What you'll need to do is measure the central frequency and one edge or the other. This is just like we did with Andromeda. We didn't measure with Andromeda because we had certain bands. And so for the central frequency of Andromeda, we took the central frequency of the central band. Here, we're going to measure it. So you go to live spectrum, there's a magnifier tool, you can zoom in. And the green one, we didn't have complete cancellation of the undulation, so it's on a little bit of a slope. The red one's a little bit better. You can see the horn-shaped profile, so it's a very well-ordered disk. And the central frequency for these appears to be about here. I'll write that down. For this particular observation, I'm getting about 14.7. Have to interpolate a little bit here. And for the edge, you could take either this edge or this edge. It doesn't really matter. This edge appears to be around 14, 15.7 also perhaps. Okay. Anyway, you'll make your own measurements. And this is one of the more difficult ones. It's a little bit hard to see, but it's there once you know what to look for. Okay, once you get those 2 frequencies, we can do calculations. So let's see, that was the needle. So in the spreadsheet, go to the tab for the needle. Each galaxy has its own tab. Okay. Your team name goes here. This is just like we did with Andromeda. The center frequency goes here. I just measured 14.7. The edge frequency, one edge or the other, I measured 15.7. Those are in megahertz. You do your own measurements and it will differ for different galaxies. And even for this galaxy, you'll probably get slightly different numbers than I did. Okay. And then let's do the calculations. First thing is the line of sight velocity. So you take the central frequency, you plug it into the Doppler equation. It's right here. We also have it here under the dot cam from before. The velocity divided by the wave speed is essentially the change in frequency divided by the frequency. Or more precisely, here it is, the velocity is the speed of light times the emitted frequency minus the observed frequency divided by the observed frequency. I'll type the equation in like I did before. The velocity is equal to the speed of light, 3e to the 5, times the emitted frequency, 1420.4 minus the observed frequency, and you divide by the observed frequency. With wavelength, you divide by the emitted frequency. If you're calculating the Doppler velocity with wavelengths, you divide by the emitted wavelength. If you're doing it with frequencies, you divide by the observed frequency. Let's click on it as well. So something like that. Again, delete this. You can do your own calculation. Distance to the galaxy. We know this because we observe stars of known luminosity, variable stars that we can say, oh, that's that kind of variable star, Cepheids. They have known luminosities. So we measure the brightness and calculate the distance. It's one of many techniques. So we know the distance to this galaxy. We measure the line of sight speed. One thing you'll notice with all of these galaxies, they're all moving away from us. They're all redshifted. Andromeda's blue shifted. It's moving towards us. We're gravitationally coupled. We're going to collide. But all these other galaxies are moving away from us. And the farther away they are, the faster they're moving. And we see this with pretty much every galaxy in the universe. The farther away it is, the faster it's moving away from us. And that's because the universe is expanding. Let me put up a figure here. So this is just a schematic, but on the x-axis, we have the distance away, measured by various techniques. That's the hard thing to measure, actually. And on the y-axis, we have the recessional speed, how fast it appears to be moving away. And there's a linear relationship. And this is called Hubble's law, and it's simply due to the expansion of space. These galaxies are actually not moving away from us. Space is expanding, pulling them away. And so points that are farther apart appear to be moving faster, and points that are closer in appear to be moving slower. Because the rubber band, the universe, if you think of it as a rubber band, it's just stretching at a constant, well, relatively constant rate. So there's an equation for this. I'll put up the dot cam. So velocity is Hubble's constant times the distance. So Hubble's constant is the velocity divided by the distance. Velocity is measured in kilometers per second, the distance in megaparsecs. So Hubble's constant is measured in the weird unit of kilometers per second per megaparsec. But its value is around 70 kilometers per second per megaparsec. Now, just one galaxy is going to give you a very crude measure because that galaxy may be being tugged on by nearby galaxies, which may make it go a little bit faster or a little bit slower. Anyway, you're going to measure it for your one galaxy, as will everyone else in the class. And so Hubble's constant, it's written here as well, but it's just the recessional velocity there divided by the distance, which I've provided. And each galaxy, it has its own different distance. Here's the hamburger at 11, Sculptor at 3.5. Anyway, we take that ratio, and that will give you Hubble's constant from a single galaxy. And everyone in the class will do it. If you come over to this last tab, Hubble's constant, it will find the median value for everyone in the class for each galaxy, and then it will take the median and the average of all of these. And you should get a number, even with only a handful of galaxies, you should get a number pretty close to 70 kilometers per second per megaparsec. You can measure the expansion rate of the universe, even with this very small sample. So see how close you get. That's the first part of the calculation. The second part is the same as we did for Andromeda. Now, for the most part, we're going to weigh the galaxy. So from the edge frequency that you got from the spectrum, either this edge or this edge, you again calculate a Doppler velocity. I write the equation. Speed of light, 3e⁵ times, it's right here, the emitted, 1420.4, right there, minus the observed, in this case, the edge frequency, divided by the observed. And you have to have all the numbers in there, and something will pop in there for you. And that's the edge, and here's the velocity of the center. So the rotation velocity is the absolute value of the difference, the edge minus the center, and you'll get some value for how fast that galaxy is rotating. For Andromeda, is 200, 300 kilometers per second, something in that range. You can see with these other more distant spirals. And then we're going to try to weigh the galaxy. And again, to weigh the galaxy, we need to know two things. We derived this in the previous video. We need to know the rotation speed, and we square it. And we need to know the radius. How fast is it rotating out at that distance? Tells us how much mass must be interior to it to make it rotate at that speed at that distance. Divide by g. So the radius of the galaxy, with Andromeda, we measured it in our image as an angle and then calculated the physical radius. These, we can't resolve them. They're so far away, we can't resolve in the radio. So what you would do is you would take a picture in the optical. And you've done this with galaxies. A simple enough thing to envision. Just take a picture of the galaxy in the optical, and you can measure the angular radius, and given the distance, you can calculate the physical radius. Since you get the idea, I've just given you the physical radius in kilometers. For each galaxy, it has a different size. You can see it there. The needle's pretty big. So 1.2 times 10 to the 18 kilometers. And that's all you need to calculate the enclosed mass. Again, it's that velocity squared times the radius divided by Newton's constant, 6.67 e to the minus 20. And that will give you the enclosed mass in kilograms. And we want it in solar masses, so divide by the mass of the sun in kilograms. It's right here. And that'll be the mass of this galaxy in solar masses. Remember, with Andromeda and also with the Milky Way, you get a few 100 billion solar masses, and you can check these other galaxies. They're similar or more massive or less massive, but your team was assigned to do an easy one and a difficult one, and you're going to weigh them, and you're going to measure Hubble's constant. As a class, get a good value for Hubble's constant. Okay, that's it for this video.